So here we're going to talk a little bit about acid-base chemistry in surface waters, and pH is often thought of as a master variable in surface waters as it really determines who can live in a body of water and then what sort of chemistry goes on there. So the pH of natural water ranges from between 4 and 9, with 7 being neutral. So just to kind of step back and maybe prepare yourself for your exam, you can remember that the pH is equal to the negative log of the hydrogen concentration. So if pH equals 6.8, then what is the concentration of hydrogen ions? So you might want to pause, think about that. And the answer is 10 to the negative 6.8 moles of hydrogen per liter. Okay. So if this is a little bit confusing for you, here is a link to a video. I've also posted it on Blackboard that will review how we go between exponential exponents and logarithm equations. Okay, so the second thing that becomes important with this acid-base chemistry stuff is to remember that to think about the mass action law, and then also remember that the mass action for water is a special case. So in case you wanted to see the derivation of that, here it is. So here is our equation with water disassociating into hydrogen and hydroxyl. And here's what that mass action equation would look like if it were a normal one. So with our reactants on the bottom, our products on the top, and K being equal to this number right here. But the concentration of water is a constant, as we talked about before in class, 55.4 moles per liter. So by convention, we include that number in K. And doing that looks like this. So we have 55.4 on the bottom. Instead of keeping that on the bottom, we just move it over here and multiply it by the equilibrium constant for water, which is 10 to the minus 14. Which is what you've been using in class. Okay, so using this equation, and if we know that the pH is 6.8, then what is the concentration of OH, or hydroxyl? So you can use those two pieces of information to figure it out. And you can pause and do that. I encourage you to, it will come up again. And here's your answer. Okay, so in pure water, where there's nothing but water, water disassociates in equal concentration, so there's an equal amount of hydrogen and an equal amount of hydroxyl, so that the pH is neutral. But surface waters contain all kind of stuff. It has acids, and acids being things that ionize in water, producing hydrogen and a complementary anion. And anion, in case you don't remember, is a negatively charged ion. And then it may also have bases, things that ionize in water, producing a hydroxyl and a cation. And a cation, if you don't remember, is a positively charged ion. Okay, so there are kind of different classes of acids and bases. So there are strong acids, which disassociate completely, so that 1 mole of nitric acid in water disassociates into 1 mole of hydrogen and 1 mole of nitrate. And we have strong bases that do the same thing. So 1 mole of NaOH in water disassociates into 1 mole of sodium and 1 mole of hydroxyl. So weak acids and weak bases disassociate incompletely, and two of the most important ones, weak acids anyway, are carbon dioxide and organic matter. So when CO2 dissolves in water, we end up with the carbonate-bicarbonate equilibrium system of equations. And you may have seen a figure like this in some of your previous classes when they talk about ocean acidification. And this is sort of a simplified diagram of what goes on. What's a little more complicated is these series of equations. So we have CO2 dissolving in water, making carbonic acid. And then here is the equilibrium constant for that. It's a little bit different from Henry's law constant, as it is the concentration of carbonic acid in the water divided by the partial pressure of CO2 in the air. So a little bit different from the equilibrium constant, and a little bit different than Henry's law constant. And then we have the equilibrium equations for carbonic acid, which produces bicarbonate and hydrogen, and then the bicarbonate, which dissociates into carbonate and hydrogen. So we'll do a little bit more work with this in class that shows us kind of how this works and what the implications of this are, but I just wanted to introduce it here. So we know that CO2 reduces the pH of water below 7, but there are other things in there. The big other one is dissolved organic matter, which are weak acids, and this includes things like leachate from detritus and leaves, exudates from organisms, root exudates and bacteria, for example, worms even, soluble materials from the lysis or a splitting of dead cells, and then weak acids, things like humic and fulvic acids that are very decomposed organic matter. And that's really, these things are what give us this brown color in forest waters. Other sources of things that reduce pH, you've probably talked about in other classes, so emissions of sulfur dioxide and nitrogen oxide from incomplete fuel combustion react with rainwater to produce strong acids, so that disassociate completely in water into their component parts. But we have had some success with acid rain lately. So this is a coal-fired plant in the Ohio Valley. And what we get from this is acid formation and this brown haze from the sulfur dioxide that becomes released. But then lately we've installed these scrubbers at the base of Georgia. This is one at the base of Georgia's power plant, and they remove up to 95% of the sulfur dioxide in the plant's exhaust gas. So this has been a really sort of dramatic change in our air quality, and you can see that here in the series of pictures that is showing you the concentration of sulfate wet deposition over time in the 80s, early 90s, and late 90s. So you can see pretty dramatic reduction in sulfate wet deposition. But we really haven't seen the same sort of decline for nitrate wet deposition, so that is still pretty high throughout, especially throughout the Northeast, and that's actually had some really interesting implications for tree growth in our areas that you can ask me about if you're interested. Okay, so the main points so far are that we can find the concentration of hydrogen and OHs or hydroxyls just from knowing the pH and the K or equilibrium constant of water. And that surface water pH is really determined by a lot of these weak acids, CO2 and the carbonate-bicarbonate equilibrium dynamics, dissolved organic carbon, and strong acid deposition. And there may also be other pollution, things like acid mine drainage and things that aren't quite as common but can still have a really big effect. Right, and that's it for acid-base chemistry.